Alright, welcome to Computer Science 305, and today, programming languages. Today we will be talking about both syntax and semantics of programming languages. And so, essentially, this is a concept where we're looking at equivalence of grammars as well as issues with grammars themselves. And so, if we see here, we have three different grammars, and effectively these things are all equivalent, right? It's basically a language. Each one of them is a language consisting of three types of variables, A, B, and C, separated by minus signs. As we can see, they all they're effectively the same. Well, equivalence of the grammar and what the grammar can do becomes a different concept. The interesting thing is, as we can see here, although they are equivalent in what they can describe, they are not equivalent in the way they generate a parse tree. And this is going to become very important as we talk, as we move forward. All right. So why does this matter, right? Well, the structure of the parse tree corresponds to the semantics of the string it generates, right? So parse trees, and they're depending on how they the recursion within them, as well as their underlying structure as generated by the grammar, will actually make it more difficult to understand, as well as make the actual grammar harder to design, right? So the parse tree, as it states here, is where the syntax meets the semantics, right? It's where these two things come to a head. So today what we're going to be talking about, in this specific lecture, we're going to walk all the way down through operators, precedence, associativity, and other ambiguities. And for the next lecture, we'll leave cluttered grammars, parse trees, and EBNF, as well as abstract syntax trees. So first thing we want to talk about is operators. So there's special syntax for frequently used simple operations, such as the basic mathematical operations like addition, subtraction, multiplication, division. Operator, right, refers both to the concept of a token as well as the specifying the actual operation, right? The operation itself. More often than not, these concepts are predefined. They are built into the language. For example, in Java, they are built-in constructs. We cannot add or remove operators. We only have the ones that are predefined. But in C++, Groovy, I think even C# allows you to redefine or add new operators that weren't there before. They're usually represented only by a single token, but that's not always the case, and we'll talk about that. For example, the ternary operator is actually multiple tokens separated, but it's a single operator in itself. So operator terminology, right? So operators, operands are the inputs to the operator, right? For example, when we want to add two numbers, the operands are one and two, are the numbers themselves, while the operator is the addition sign. Unary operators are ones that only take a single operand. Binary take two, and ternary operators take 3 operands. I've never seen a quaternary operator, but I'm sure they. No, I can't actually think of any language where they exist. So pretty much this is what you'll. The worst case you'll see will be a ternary operator. There's different types of ways that operators have been used in languages in the past. The infix is what we typically see. This most common. It's where we put the operator in between its operands. But prefix does exist, as I showed in Lisp the other day when we were talking about the historical languages. Lisp uses a prefix notation, right? The operator comes before the operands. There is a postfix notation. I can't think of a language off the top of my head that uses postfix, but it is a possibility. Oh, there we go. The postfix operation A++, right? In Java, JavaScript, C, C++, and a variety of the C-derived languages. have the postfix operation. They also have a prefix version where it's like plus plus a. These types of operations are common, but not common across in those languages across all the operations, right? Only a few are defined in such ways. So then this brings us to precedence, right? So precedence is, we can think about this as how we interpret which operators will be calculated first when we're actually interpreting the language. And so we take this example grammar, G4. And so it's a grammar made up of expressions and the operations that can be performed on them. So if we allow, and then of course the three variables A, B, C. So one of the major issues is how do we define precedence? Which operations have higher precedence over others? So if we take a look at this, this grammar that G4 generates the tree that we see here, and basically what it's showing us is that if we were to process this tree, the addition between A and B would happen before the multiplication of that value in C. And so this is contrary to the notion of how we typically think of precedence in mathematics. Typically in mathematics, we want to say that multiplication has a higher precedence than addition. So what actually should happen is the value should be B the product of B times C should be added to A rather than the summation of A and B multiplied with C. So what we need to do is we have to understand how operator precedence works. It basically applies when the order of evaluation is not completely decided by parentheses, right? So although we could easily use parentheses to have the highest precedence and then allow that to control, but we shouldn't have to add parentheses at all times. We should have an understanding of the precedence order, right? So as it's saying here, each operator has a precedence level, and those with higher precedence are performed before those with lower precedence as if they were parenthesized. So we expect to see A plus B times C equivalent to A plus the grouping of B times C. And so, and that is reflected in almost all languages, and that is stating that without the parentheses, multiplication has a higher precedence level than addition. Now, there's all sorts of different examples of precedence. Languages have all different levels. C had 15 levels of precedence, right? Possibly too many. Pascal had 5 levels of precedence, possibly not enough. And then Smalltalk just said everything, all binary operators have the same precedence level. It's your job as a programmer to correct that with parentheses as necessary. So the interesting thing here is that depending on who you are and what you believe, you can think one thing or another. It's my opinion that you should be aware of all this with whatever language that you use. In our grammar that we've been looking at, we had that precedence problem. And so our goal is to change this such that the star happens, the multiplication is a higher precedence than addition. And so how we do that is we need to shift, when in the parse tree is generated, we need to shift it so that multiplication is deeper in the tree than addition. And that can be achieved by grammar G5. And so what we did here is we took the multiplication expression, so all the things that follow addition in the original grammar, and we create a new rule that has all that occurring after, so it has takes all that part and puts it into that rule. And so this gives us the capability to have these precedence levels. Now what this will say though is that parentheses is on the same precedence level as the expression, right? As multiplication, I believe. Don't quote me on that. That might be incorrect. So as we can see, once we've done that, right, what has happened is we've shifted for the A plus B times C. We've shifted the multiplication down to a lower level than plus, such that b times c will be evaluated prior to a plus that product. So now it's correct, at least for these two. So this gets us into associativity. So associativity, right, is the second issue with this grammar. So let's say we have our grammar G5, the one we just modified to fix the precedence ordering, and it can generate either of the two trees for a plus b plus c. So this is another issue that we'll talk about, but the main one that we were focusing on right now. And so if we look at this, the first one, right, is not how we would expect it to occur. We expect to have left associativity. That is, we start from the left and work towards the right. Whereas the second associativity is right associative. So in order to deal with this, right, we have to think about what is this. Well, so associativity applies when the order of evaluation is not decided by parentheses or by precedence, right? So in the case that, so now we're looking at any types of operators on the same level of precedence, and when we don't have parentheses, but we want to evaluate as if the correct parentheses were there. And so, for example, left associative operators group left to right, as I was talking about. So what that does is essentially we want, if it's a plus b plus c plus d, we effectively want to be the sum of a plus b, that sum plus c, and that sum plus d. And that's what the parentheses show us in the second bullet point. In the third bullet point, we're talking about right associative. That means we start grouping from the right. So instead, we interpret it as the sum of c and d plus the sum plus b, and that sum plus a. And so we don't really want, that's not how we think of math typically. We think from left to right, similar to how we read in the English language. And so we need to figure out a way to deal with this, right? And so most operators in most languages are left associative. There are a few exceptions, and we'll talk about that. But the goal here is how do we figure out how to make this happen? So some examples of this: most operators are left associative, right? So the first example in the C is the right shift or the left shift operator, where we're shifting the bits from C into B and into A. Really, what's happening is we shift from B to A, and then we shift into that C. Same with assignment. Assignment, on the other hand, is right associative, right? We're going to start from the right. So we assign 0 to B, and then we take that, whatever the value of B is, and assign that to A. In ML, as we'll learn, most operations are also left associative, right? 3 minus 2 minus 1. So 3 minus 2 is 1, minus 1 is 0. The second operations, this is cons. The double colon is called the cons operator in ML. And basically what we're saying is we want to, we're going to build a list, so we have to start from the right. And so each one of these cons operators, basically what it does is it pushes that item onto the front of the list. And so we initially start the list out with nothing inside of it, nil, and then we put ahead of that 2, and then ahead of that 1. So our list that we generated would essentially be 1, 2, and then nothing. So the list is just 1 and 2. In Fortran, right, most operators were also less associative, which was A divided by B multiplied by C, right? So that would be whatever the quotient provided by A divided by B, and then that multiplied by C. Whereas on the other hand, we have the exponentiation operation that's right associative, right? I want to see what the exponent of B and C, of B to the C power is, in order to use that value to then raise A to that power. So when we come back, now bringing all this back into the grammar, right, we're looking at G5 again. To fix the associativity problem that we had, we need to modify the grammar such that we grow the tree of pluses down and to the left. Okay? and we want to do the same for the multiplication operators. And so how we're going to do this is essentially we need to have recursive items. So for a given rule, like for example in G6, with the first rule exp, its first item is exp plus then the multiplication rule. And so the interesting thing about this is we want the same rule on the left. For a left associative, we want the rule that we are currently looking at to be on the left side of the operator. So that's why it's there. And this will actually create a left associative growth. On the other hand, and then we have the multiplication rule on the right side, or it's just multiplication in the case that we're looking at a star operator, right? So in the second rule, mulx, what we're looking at is, again, to make this left associative, we have the recursive rule, so calling itself, on the left side, and then we have the new rule root on the right. And so what that gives us is the capability to create this right associative. And then the right side, the root rule, has everything remaining after the multiplication that was in G5. So this gives us the capability to build left associative rules. The opposite would be is if we want to do right associative, we do the opposite, right? We put the recursive rule on the right side of the operator rather than on the left. So our new grammar, right, generates as expected, right? Generates the correct tree for A plus B plus C. It generates the same language as before, but no longer generates trees with incorrect associativity. That's the whole point. We want to make sure that, and we'll talk about this shortly here, I'm sure, is that we want to ensure that we're only generating one parse tree, and that's the correct parse tree for what we're trying to say. So here's a practice section, and what I want you guys to do is go ahead and take the grammar G6 that we have here, pause the recording, and then attempt to add a left associative ampersand operator at a lower precedence than all the others. At the same time, add a right associative exponentiation operator, double star, at a higher precedence than any of the others. So then we'll talk about this at the beginning of the class, and we'll see what your thoughts are. Alright, so those are what we call ambiguities, right? Whenever we generate a tree, a parse tree that has what we'll call that has the capability of generating more than one tree for the same input string, that's called an ambiguous parse tree, and thus making the grammar ambiguous. And so that's what we're talking about, like I just said. So G4 was what we wanted to call ambiguous, right? And generating more than one parse tree for the same string. Fixing associativity and precedence problems eliminated all the ambiguity. Basically what we're saying is that there's no way for any possible string in that language that it could generate more than one parse tree using that grammar. And that's the goal, right? So if we want to test for ambiguity, we have to be able to show that that there is a possibility it will generate more than one tree, and that can be done simply by proof by example, right? If I can show two different ones, that's good enough to show it's ambiguous. Now that means that you have to fix it, but we can start breaking it down based on associativity, precedence, and there's a few other things that we'll talk about. One of them is what we call the dangling else problem. So we don't. So typically, like it says here, the parse tree corresponds to the meaning of a program, and thus we don't want any ambiguity about it, right? Ambiguity in meaning makes for confusion, and worst part is it confuses the program, as well as the results don't come out the same every single time, and so that confuses the developers and programmers that are using your language. But as stated here, not all ambiguity comes from precedence and associativity. So this is the problem of the dangling else. So let's say we have a grammar for an if statement, right? And it's very simple grammar. It can either be the if statement or S1 and S2. The if statement breaks down as if, then an expression, then a statement, else statement, or it can just be if, expression, then statement. and then an expression is just E1 or E2. Well, the problem here is we have two different versions of if, one with and one with an else and one without. The problem becomes if we just have an else hanging out there, and we have a nested if statement, which if statement does it belong to, right? So if we take a look at the statement we have down below, it says if E1 then if E2 then S1 else S2. The problem is if we look at these upcoming two trees, we don't know necessarily which if statement the actual else belonged to, right? It could belong the top tree shows that it belongs to the first if statement. The bottom tree shows it belongs to the inner if statement. So most languages that have this problem choose the bottom parse tree, right? They'll just match the else with the nearest unmatched then, and that's one way of solving it. But the question is it the best way? And so we can actually eliminate this ambiguity, and this corresponds to this the then with the statement, right? This is how we're going to take care of this, right? We have so we're saying that if it expands into an if, the statement that's highlighted, then that if must already have its own else. First, we're going to make a non-terminal full statement. Okay, this is how we're going to fix this whole thing. The full statement says that generates everything a statement generates except for it cannot generate an if with no else. So basically, we're saying that the inner if must have an else. All right. Well, that's grand, but limiting. So that's what we've done here, right? Now we have this full statement. Then we use the two. Then we use the new non-terminal there, right? We replace it, and the effect is the effect becomes that a new grammar cannot have. In the new grammar, we can match an else part with an if part only if there is only if all the near if parts already have been matched. So that handles and it creates the correct parse tree, which would be the inner the else is matched with the inner if rather than the outer. Well, that's great, got rid of the ambiguity, but the question is that really going to do what we want, right? And it's doing exactly what it says. The grammar trouble reflects a problem with the language, which we actually didn't change. We didn't change the language. We just added we just modified the grammar slightly, but this is going to make it difficult for people to read, and it also will make it very confusing for individuals who are trying to program this. So the question becomes, if we have this statement here, what is the value of A after this fragment executes? So I leave that to you to determine, and we can talk about it at the next test. So this will be another part of what we talk about in the class. So I'd be prepared with answers to both these two practice experiences prior to coming to class for that first 10 minutes of class. So, interesting enough, in many languages, they have another way of handling this problem. For example, in Python, if you create an if statement, you have to indent, right? So, as long as we can figure out exactly where the else belongs if it's indented with its if. And that's how Python handles it. A better approach, though, is through the use of block structuring. So in all the C languages, Ruby, Java, C#, all these different languages, they have what they call block statements. So an if, following an if, the then part is essentially a block, and that block then can contain any type of statement. Right, and so we in C-derived languages like Java, C#, C++, etc., they use curly braces to represent a block statement. And so within that block, there can be anything, and we don't have to worry about the dangling else, because as long as the else is still within that block, it cannot be a part of the outer if. In Ruby, we use blocks that are started with a bunch of different keywords like if, while, unless, until, etc., and they all end with an end statement. So as long as we haven't hit an end, we know that we're not part of that outer. We know we're still within the inner block structure, and thus we have for example, on the inner if, right, it will have an end statement for itself. That end denotes that we're done. So if there's an else outside that, it must be a part of the outer if. That's how we know. And anyway, so that gets us into languages that don't dangle, right? Some languages find the if then else in a way that forces the program to be more clear. Algol allowed the then part to be another if, though it could not be a block containing an if statement. Ada required if statements to be terminated with an end if, right? So they used a block. And then Python requires nested ifs to be indented, right? Which I already talked about. It's just everything that is inside the if is indented in a certain to a certain level. So if an else is inside there and it's indented, then it's not part of the outer if. Okay, so that brings us to the next set of lectures. So I'm gonna stop that here. And I look forward to talking to you all in class. Be prepared with answers to those two practice parts. So we'll see you then.